So far, we have already discussed about the damped harmonic oscillator and also the simple harmonic motion. In this class, we will learn about the forced oscillator, forced mechanical oscillator. As we know that in calculus, x is represented by the displacement, velocity is represented by dy by dx, that is the rate of change of displacement, and d2x upon dt square is represented by acceleration. In short, the x is displacement, dx by dt is velocity, d2x upon dt square is acceleration. All are the vector quantities. Now the equation of the forced mechanical oscillator is given by d2x upon dt square plus r by m dx by dt plus k by mx is equal to f naught e to the power I omega t. This is known as f naught e to the power I omega t is known as a driving force which are applying again and again. In this there is a simple example of the cradle, and we pushing force or pulling force apply to slip the baby well. Now it is all clear that K by M is the factor of the stiffness constant or stiffness constant or the spring constant which affect the displacement. X is the displacement and the R by M is the damping factor, damping term, and damping term affect the velocity. dx by dt it affect the velocity. And now d2x upon dt square, this is the equation of the forced mechanical oscillator. It is clear from the equation that the damping term R by M affect the velocity of the system and the stiffness term, that is the K by M, affect the displacement of the system. K by M, here we are denoting it K by M for the spring constant or stiffness constant S. The figure is like this. There is a spring, this is the fixed part, one part is fixed, and this is the spring connected with the another force, another parts, which is when we applied force, this became starts a movement in to and fro in simple harmonic motion. Now we will discuss at any instant of time works three factors. First factor is known as the restoring force minus k by x, and second term is damping force minus r dx by dt. R is damping constant and deriving force F is equal to F naught e to the power I omega t. The negative sign in the above equation indicates that the force works against the displacement. Solution of the forced mechanical oscillator, that is equation first, the damped oscillator affect the driving force in two ways. First one is transient behavior and second one is the steady state behavior. So we will first discuss about the transient behavior. In transient behavior, after some interval of times, there is a microseconds, the applied forces disappear, and so the force became zero. The m d2x upon dt square plus r dx by dt plus kx is equal to 0. This is the, in this case, the system behaves just like the damping, and the solution of the x is given by a e to the power I minus rt by 2m cos k by m minus r square 4m square per power half t minus 5. It can be also written as x is equal to e to the power x is equal to a naught e to the power minus rt by 2m I into k by m minus r square divided by 4m square per power half t minus 5. The real part, it has two parts, as we know that exponential term. There is an exponential term. It has the real part of x gives the actual solution. Here x decays exponentially with time. It is the case of a lightly damped oscillator in which r square by 4m square is less than k by m. We have already discussed in the previous case, that is the stiffness term dominates over damping term. The frequency is given by f dot is equal to omega dot divided by 2 pi, that is 1 by 2 pi into k by m minus r by 4m square per power half. This is the frequency. In steady state behavior, the damping in the steady state behavior, depending upon the magnitude of damping, the transient transient oscillation die down, and the external driving force dominates the oscillator. The displacement in this state is the solution of equation first. Let the solution is x is equal to e to the power I omega t. Differentiating twice with respect to time, we have the dx by dt is equal to a I omega e to the power I omega t, and d2x upon dt square is equal to a omega square e to the power I omega t. Substituting this in equation first, we have minus m omega square a plus I omega r a plus k e to the power I omega t f naught e to the power I omega t, and this is cancelled out. Then we have a omega I r plus k omega minus m omega is equal to f naught, and a is equal to f naught divided by w omega I r plus k by omega minus m omega. Equation number 4. Multiplying and dividing the right hand side by minus I, we get a is equal to minus I f naught, and omega divided by omega into r plus I m omega minus k by omega. Equation number 5. Writing r plus I m omega minus k by m is equal to zm, that we can write the equation 5 as a is equal to minus f naught omega by zm. Here zm is equal to r plus I into omega m minus k omega is called mechanical impedance of the oscillator. It consists of two parts. First are the resistance to the oscillatory motion due to friction or the viscosity, and kappa m is equal to omega m minus k by omega, the reactance to the combined effect of inertia and elasticity. Here omega m is the inertial reactance and k by omega is the elastic reactance. Multiplying with m, the equation may be written as m d2x upon dt square plus r dx by dt plus kx is equal to f naught e to the power I omega t. Thanks for watching.